Hi, in this video we will introduce a new notion for subspaces. It's called a basis. Well, intuition behind this is easy to understand. Well, consider an example, R2. We know that R2 is a span of different sets of vectors. For example, span of these vectors will give you R2. But someone can come and add another vector to this list. For example, I can say that, well, you see 2, 1 added to this. The span will be the whole subspace, is the whole space R2 still. We added one vector to the list of spanning vectors, but still we get the same thing. As you see here, the set of vectors which span some space or some subspace may have some extra vector in it. So here we really don't need this guy. This is an extra cost. We are interested in minimal set of vectors which generate or which span the space. Minimal meaning that if you take one of these vectors out, the spanning subspace will be smaller than what we have. For example, look at this guy. I can take this one, but still we have the same thing. But for these two, if I take any of these guys, we won't get R2 as the spanning subspace. Yes. So we want to make it somehow minimal. And this is where the set's basis comes in. A basis for a subspace S of Rn is a set of vectors. Well, I will denote that by curly B. So it's a set of vectors such that, so it has this property such that 1. So it spans the whole S. So S is, in other words, span of the vectors of B. The second thing is that we want that to be minimal, meaning that we won't be able to cancel or take out any of these vectors and have the span, the S as the spanning set. Well, that is written in this form. B is linearly independent. You see, if a set of vectors are linearly dependent, one or some of these vectors can be written as linear combinations of the other ones. So if I can cancel, if I can take that out, still the spanning set will be the same thing. Linearly independent sets are the minimal sets that generate that spanning set. Okay? So these two things, you have to always check these two conditions. Span the whole thing, and the vectors in the set are linearly independent. So we will do some examples here. Okay, determine if the given set is a basis for the given subspace or space. Okay, here in this case, I have two vectors for R2. Is it a basis for R2? What should I check? I should check that, first of all, span of these two vectors is equal to R2. In other words, we have to check every vector xy can be written as linear combinations of these guys. And as you know, it is equivalent to solving this guy for having solution for all xy. So here I can add row 2 plus row 1. And then we get 0 here, 2 here, x plus y. And here's 1, 2, x. And well, this is row echelon form, and as you can see, this is consistent for all x and y. No matter what is x and y, we don't have any zero row which can be equal to non-zero. So for every x, y, we have a solution. That means that yes, this guy is in the span. The second thing we have to check is that they are linearly independent. So 1, -1, and 2, 0 are linearly independent. And that one you can check by seeing if the homogeneous system has unique solution or not. Yes. So here what we do, again, do the same work. Actually, I could have said x can be equal to 0, y equal to 0. So in this case, you see that this is 0, 0. Well, we have 1 leading entry, 2 leading entry. Each column has one of those, so we have only a trivial solution. And trivial solution means that the columns are linearly independent. The vectors are linearly independent. Okay. Very nice. How about this one? Okay, so we have 2, 2, 1, 3, 4, 0. Is it a basis for R2? We have to check if they span the whole R2 and if they are linearly independent. Well, let me just tell you something about linearly independent. Remember, the set of vectors with 2 components, any set of vectors which have 2 components and have more than 2 vectors are linearly dependent. So 2, 2, 1, 3, 4, 0 is linearly dependent. You can find different reasons. For example, another reason would be that if you find a row reduced echelon form of the augmented matrix 2, 2, 1, 3, 4, 0, 0, 0, this is definitely consistent because the trivial solution is always there. But at the end, we are going to have at least one column which doesn't have leading entry. That means that that will be a parameter and that will have infinitely many solutions. That means that we will have non-trivial solution, and that's why these are, linearly dependent, and as a result, this is not a basis. Well, if you want, you can check actually this guy span of this vector is R2. So the span is R2, but they are not linearly dependent. That means that it's not a basis. How about this one? Okay, so we can start always doing one of these guys. Yes, so I want to see for y, for which x, y, z this system has solution, or it's consistent. Here I can get rid of this by R3 minus R1, which will give us 0, -3, and then this will give us -3, and then this gives us z minus x, and this is 1, 2, 4, x, 0, 1, 1, y. And well, from here you can say, okay, 3 times row 2 added to row 3 will give us 1, 2, 4, x, 0, 1, 1, 0, 0, 0, y, and then z minus x minus 3, plus 3y. And as you can see, if this guy is non-zero, this is inconsistent. So if x minus y plus 3y is non-zero, for example, take x equal to 0, y equal to 0, and z is equal to 1, then the system is, this is just an example, the system is inconsistent, meaning that it doesn't span all the x, y, z. So that means that span of the vectors, let me call this as b, is not equal to R3. Well, you could check the other condition just by trying to see if it has the only trivial solution. But as you can see here, if I set x equal to 0, y equal to 0, z equal to 0, this guy actually is going to have 0, 1, 1. Oh, sorry, I'm setting x, y, z 0. You will see that this has a non-trivial solution. It means that the vectors actually are not linearly independent. So both of the condition fails. You don't need to check the second one, but I'm just doing as an extra practice. Okay. How about this guy here? 1, 0, 0, 0, 1, 0, 0, 0, 1. Well, if you put x, y, z, well, this is already row reduced echelon form. That means that no matter what is x, y, z, it has a solution. Actually, what we know is that every vector x, y, z is equal to x times 1, 0, 0, and y times 0, 1, 0, and z times 0, 0, 1. How about independence? Well, this is the first thing, yes. Then the second thing, linearly independence. So if we have this guy here, 0, 1, 0, 0, 0, 1, for the homogeneous system, as you can see, this will mean that only trivial solution. Yes, we have only trivial solution. Because this says that the third variable is 0, second variable is 0, first variable is 0. So only trivial solution. That means that these are linearly independent. Well, that means that yes, this set of vectors are bases, and actually this is this is in general true. So let me write here is a basis. In general, let me write it as a remark, or in general. The set, you remember, we call the standard unit vectors. The standard unit vectors. So E1, E2 up to En. What are these guys? Well, E1 is the one which has 1 at the first component, everything else is 0. E2 is the one which has 1 in the second component, everything else is 0, and so on. En is the one which has only the nth component 1, everything else is 0. So these guys are bases, or form a basis, sorry, form a basis for Rn. So that's an example that you should always keep in mind. The very simple, the standard one are these vectors. The vector which has 1 at the i's component, everything else is 0. So you pick n of this, and that will give you a basis for Rn. Okay, so these conditions can be studied for Zn. Also, these modular modular integers. So again, you should look for the same result, so same conditions. First of all, the span is the whole thing. So let us see x, y. In Z5, I want to multiply row 1 by something and add it to row 2 to get 0. So if I do 3 row 1 added to row 2, we will get 0 here. 3 times 4 is 12, plus 3 is 15. 15 in this is 0. And this is y plus 3x. And this is 1, 4x. As you can see, if y plus 3x is non-zero, for example, if x is 0 and y is 1, then we don't have any solution. The system is inconsistent. That means that the span of these vectors is not the whole Z5 to the power 2. So it's not a basis. So you see, now we are just checking to see if this is a basis or not. Later on, we will figure out a way to find a basis. And in more details, we will see how this works. Let me just add one example in which we can find easily a basis. So find a basis for the subspace of all vectors who in R2 which have first component twice as the second one. So this subspace, we already studied these subspaces. So the first component is twice as the second component. So whatever the second component is, let me write as A. The first component is going to be 2 times that for all A in real numbers. As you can see, any vector in S can be written as, so 2AA can be written as A times 2, 1. And well, this means what? Means that span of 2, 1 is equal to S. And 2, 1 is only one vector. Any non-zero vector, just take any non-zero vector and put it in a set. So this guy is going to be linearly independent. So that means that, yes, we found something. 2, 1 is a basis for S. We will study these in more details, and we will find more ways to find bases for different subspaces.